Welcome to Dr. Jed's continuing series on calculus. Today's lesson, section 4.2 for Rogowski, is on extreme values. So this is if you missed class on Friday, right before spring break, naughty naughty, or if you just want to refresh on it to remember what we covered. So, what are extreme values? The first thing we're going to do is talk about what they are. They're local or global maximums or minimums. We'll talk about that. We'll find out where they exist. Then we'll talk about critical points, which are really central to this whole topic. Do you remember when I said this is the most critical part of the whole chapter? That was partly a pun. It's partly true because critical points are called that for a reason. They really are critical. Then we'll talk about how you use them to find absolute maxes and mins. We'll save local maxes and mins for another section, and then do some examples. So first, what is the definition? What are extreme values? Extreme values are maximums and minimums. Look at this curve. It goes down, then up, then down, then up, then down, up. The ups and downs, the tops and bottoms, are the minimums and maximums. So when they go to the top, those are local maximums, or maxima, that's the plural. At the bottoms, they're local minimums, or minima. And notice one of them special. This is the absolute minimum. Why? It's the farthest down the whole graph goes. The absolute max or the absolute min is the farthest down, the absolute max is the highest up. And notice, since this graph this graph keeps going up, there is no absolute max on this graph. So a natural question is, when are there absolute maxes and absolute minimums for a graph? So, to answer that question, we have what's called the extreme value theorem. Lots of words. What it says is, if f is a function that has a derivative, if f is on a closed and bounded interval, then it does have an absolute max and min. It doesn't tell you where, but it tells you they must exist. This is useful for finding it. Now, what do I mean by closed bounded interval? A closed interval includes any endpoints. So what does bounded mean? Bounded means, well, it's got endpoints. Now you think, well, if it had endpoints, then it has endpoints. But think about the whole real line. If you go on forever, well, there are no endpoints. So if there are no endpoints, it's closed. But it's not bounded because it doesn't have that endpoint. Bounded means, yes, there's endpoints, and yes, you have them. Yes, there's endpoints, yes, you have them. And how do critical points fit into this? Well, we'll define a critical point. A critical point is a place of the function where the derivative is 0, or the derivative does not exist, or d and e. Let's take a look back here on the graph. The circled little spots here. Here, 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 here. Those are places where the derivative is 0. Oh, not that one. These three and that one are derivative is 0. Here the derivative doesn't exist. Those are all the critical points. And notice how well they correspond with the local minimums and maximums. Not perfectly, because the derivative is 0 here, and yet it's not a maximum or minimum. But there's a strong correspondence between critical points and local maximums and minimums. Let's take a look and characterize it in Fermat's theorem. Fermat's theorem says, well, it says simply if you have a local max or a local min, you must have a critical point there. And as we saw, it doesn't work both ways. If you have a critical point, it might not be a local max or min. So if you have a critical point, it might not be a local max or min. But if you have a local max or min, it has to be a critical point. But our big question right now is not this, but global maxes and mins. Well, it turns out local maxes and mins are really good contenders for being the absolute biggest. If you talk about being the highest for a while, well, the highest ever is kind of like the highest for the while. So we look at the critical points, but we add one other thing to it. So finding an absolute min or max on a closed bounded interval. First, we find the critical points, which we just talked about. Then, another choice is endpoints. Look at this graph right here. Goes down, goes up, goes down, goes up, and ends. The minimum turns out to be right there at a critical point, but the maximum is right there at one of the endpoints. If it goes and stops, if the graph just stops there, that could be the biggest or the smallest. Now how do we tell if it's the biggest or smallest? On a closed bounded interval, we know there is a biggest, there is a smallest. So just plug them all into the function, see which one's biggest, which one's smallest, and then that's our answer. Let's see if this makes sense with an example. So here's a function. x cubed minus 3x squared, minus 9x plus 1, and a closed bounded interval. I want to find the absolute min and absolute max on this. Well, the first thing to do is look at the critical points. And what are critical points again? Critical points are where the derivative is 0 or doesn't exist. So it's where the derivative is something. So we need the derivative. Let's take the derivative. Hopefully you're not going to be panicked by this particular derivative. You can do it. 3x squared minus 6x minus 9. Now we need to know where that's 0 or where it doesn't exist. Doesn't exist has to do with things like, well, divided by 0 or errors, square roots have some issues. This won't have an issue. It's a polynomial. You can plug any x in there you want. The domain is everything. So does not exist is going to not give us any information. It's not a bad choice. It's just not, in this case, going to have anything. On the other hand, equals 0 will yield some results. How do we solve that? We factor. I can factor a 3 out of that. And then, see, that makes x squared, 9. Well, if I'm pulling the 3 out, I have a minus 3 left over. If I have a minus 3 left over, how do I multiply to get minus 3? I get like a 1 and a 3 or something. So how do you do this? Well, it turns out that's how you factor it. And those multiplied together equals 0. The magic of 0 says, well, that means one of these three things is 0. And of course, 3 equals 0 will not yield any useful results. That's just, it's there, but it's not true. Nothing will make that true. This, however, x equals minus 1, or x equals positive 3. Those are the critical points for this function. But remember, we want this particular interval. We only want critical points that are in that interval. So this one's not useful for us. It is a critical point, but it's not in our interval. So how do we now find which is the biggest spot on this interval? Which is the smallest? We plug it into the function itself. Not the derivative, but the function. Plug this in there, and plug the endpoints. If I put 2 in here, that's what, 8 minus 12 is minus 4, minus 18, so minus 22, plus 1, so minus 21. Put minus 2 in, minus 8, and minus 12 more is minus 20. Minus 20, now minus minus makes plus 18, so that's minus 2. Plus 1 is only minus 1. Those are both negative. They could be the answers. It could be this is a false one. But let's try it. Minus 1 cubed is minus 1. Minus 3 more, so that's minus 4. Minus minus, so plus 9. So minus 4 plus 9 is 5. Plus 1 is 6. This is the biggest. It's absolute max. This is the absolute minimum. And there you have it. That's how you do it. Now, if you don't have a closed bounded interval, sometimes you have to do something else to figure it out. So our next example, we'll take a look at a function on, this is a closed interval, but it's not bounded. It does not have its endpoints because there are no endpoints at infinity and minus infinity. Those aren't numbers. They're just, well, directions towards infinity. Again, the first thing we do is take the derivative. You would use the quotient rule to find this. So it's the derivative of the top, which is 0, minus, well, it doesn't matter. So minus the derivative of the bottom, times the top, over the bottom squared. Now, that's the derivative. We want where that's equal to 0, or now, doesn't exist where a fraction is reasonable. It means the bottom is 0. Equals 0 is also reasonable. It means the top is 0. When you have a fraction as your derivative, and you want to check this out, critical points are where the top is 0, or where the bottom is 0. Now, hopefully you can see quickly, this means x equals 0. That is a critical value, critical point. This one, x squared, well, x squared can't be negative. Add 1. Now we've got something positive and we're squaring it. There's no x's, not on the real line at all, that can make this equal to 0. That will never be 0. So we only have one critical point. And in fact, we don't even have endpoints anymore. So what do? Well, we're going to have to take a look at the graph. We're going to have to figure it out. Since we don't have endpoints, we are not guaranteed a max or a min, which is good because we only have 1 point. So let's take a look. Here I'm going to draw a number line. I'm not going to look at the values of the function at the number line. I'm going to look at the derivative. At 0, well, plug 0 in here. The derivative is 0. How about for negative numbers? Say like negative 1. If I put a negative 1 in here, well, the bottom is squared, it's positive. The top minus minus, this is plus. If I put a plus 1 in there, hopefully you can see. Put a plus 1 in here, the derivative is negative. What does that tell us? It tells us a lot. Because what is a positive derivative? It means the function is always going up. What does a negative tell you? It tells you the function is always going down. There's a couple of things we can just learn from this. First of all, is there a max? Right there. This is the maximum for the function. Because over here is always smaller. Over there, it's always smaller. So there's an absolute max at x equals 0. And what is the value? Plug it into the function. And that's the absolute max for this function. What about minimums? Well, whatever I pick over here, it gets smaller as we go on. Whatever I picked over here, it would have been smaller earlier. There is no absolute minimum. The function's always bigger than 0, but it just gradually gets bigger, gets up to here, and then it gets back smaller and kind of inches its way towards 0 again. When you don't have endpoints, you have to be careful how you argue it, but sometimes it's still very, very doable. Sometimes it's a little harder. This one worked, not all of them do. Until next time, this is Dr. Jeff.